Welcome back to Physics 142. We've been talking about forces from magnetic fields, and in this video I want to think a little bit about if there's any cases that you can get a torque from a magnetic field. So you remember back from Physics 141, right, that a torque is a force that makes something rotate, right? And we had a formula for torque, so let's just write that down here. So I remember torque, we use the letter tau, and the formula for that was R cross F, right? That it basically what this said is that the amount of torque depends on the distance you are from a pivot point, the force that you apply, and the angle between them, and that angle between them we ended up representing with this cross product. So you might recall that if I have my marker here and I want to apply a torque to the marker, right, if I apply a force at some radius, then that is going to apply a torque. It's going to make the marker rotate. So the question here is, how do torques relate to magnetic fields? Are there cases where magnetic fields could give us torques? And the answer to that, of course, is yes. And a situation where we often get a torque is if you have a closed loop of current. And so I want to show that to you a little bit. And so what I want to do is let's think about some current loop, and I'll think about a rectangular current loop here. So let's imagine that I have some rectangle here. Mine's going to look pretty square. That's okay. All right, here is a rectangle wire. All right, and I'm going to run some current through this wire. So maybe I will run current, some current I through this wire. Maybe I'll run it counterclockwise through the wire. And let's give this wire some dimensions. So let's call this side length A and this side length B. That means that this loop of wire must have some area to it, right? Must have some area. So the area is going to be equal to A times B, right? That's the area of this wire. And then what I'm going to do is, so I have a wire, I've got current running in it, and I want to take and put this wire in some magnetic field, all right? So let's apply a magnetic field, and maybe I'll apply a magnetic field across it in this direction. It ends up not actually mattering, but for purposes of thinking about it, let's apply a magnetic field horizontally here to the right. Okay, and now the first thing I want to think about is I want to remember, see if we can think about, well, what are the forces acting on this wire, right? So we know that forces from magnetic fields, the forces that we had for each segment of this wire, well, would be the current running through the wire times the length of that segment crossed with the magnetic field, right? And so, well, what does that mean? Well, let's think about each segment. So this segment here, where I have current running in the same direction as B, anytime L and B are in the same direction, well, then you'll get a sign of 0, and that makes the force 0, right? So in this chunk of the wire, the force from the magnetic field will be 0. Similarly, when you're running opposite to the magnetic field, right, then again, you're not crossing it at all, and the cross product is 0. So here, the force in this segment is 0. But what about these side segments here? Well, in this segment, right, the I is up and B is to the right, and so that's going to leave my thumb pointing, can not really see this, but away from you, right, into the whiteboard. So here, the amount of force on this part of the wire is going to be I times L times B times sine of, they're perpendicular to each other, so it's times sine of 90 into the page, right? You get a force that's into the page. Over here, well, now the current is going the other direction, right? And so this is going to be a little bit hard to show, but you put your pointer finger down, you curl your other fingers to the right, and what you'll get is that your thumb will point up out of the page, all right? So the force over here on this side of the wire, the force here, all right, is going to be ILB again, but this time it's out of the page. Out of the page, all right? So we have force here that's into the page, force here that's out of the page, and so the first question we might ask is, well, what is the net force? Right? What is the net force? And, well, the answer to that, it's 0 here, 0 here, and then we have ILB into the page. We have ILB out of the page, right? ILB, if we did this from a side view, right, we would have ILB into the page, and we would have ILB out of the page, and so those would cancel, and so the net force, if we added up all of the forces, would just be 0. All right, so the net force on a current loop from a magnetic field always ends up just being 0. All right, so that's interesting. So you don't actually end up getting any net force on this current loop. All right, however, you might see that while this force is being applied on one side and this force is being applied on the other side, what that means is that while the net force is 0, but usually you get a torque, right? Because anytime you apply uneven forces, a force on this side and a force on this side, that should make the object rotate. So let's have a look at that. All right, maybe I'll draw another picture here. We'll sort of view it kind of edge on, all right, but let's see if I can draw this. So maybe if we view again my current loop at a little bit of an angle now, all right. So this is now going to be the part again where F was equal to 0. So the magnetic field is kind of coming across it like this, all right? And this will be the part where we have the downward force, all right? There was the downward force, the IBL downward. This will be the part where we had the out of the page force, all right? And then again, this part of the wire had F equals 0, all right? And so what we can see is now clearly, right, we have this down force and the up force. They're acting on different parts of the object, and so that's going to create a torque. It's going to create some rotation. And a thing that will be useful to us shortly is anytime that you have a chunk that has an area we can also represent as a vector, right? Area can be represented as a vector, and so we remember that the direction of an area vector is always perpendicular to whatever surface you're dealing with. So perpendicular, that would be either up out of this loop or down out of the loop. For current loops, we always choose the direction of the area vector to be where your thumb would point if you curl your fingers in the direction the current's flowing. So here, the current is flowing counterclockwise, right? It's flowing counterclockwise. And so if I curl my fingers in the counterclockwise direction, my thumb would point up out of the whiteboard. So the area vector here we're going to take to be in the up direction. And that will be useful in just a second, because what I want to try to argue to you is that the torque on this current loop ends up depending on that area and on the amount of current and on the magnetic field. As a matter of fact, the formula for torque ends up being the following. All right, let's write this down. The formula for the torque on this closed loop ends up being I times the area vector crossed with B. So just like the force on one chunk was IL cross B, all right, for the torque, the answer is going to end up being I times the area vector cross B. All right, so that's sort of interesting. Curious how that works, right? Maybe sort of unit-wise, we can see that, well, if the force is IL cross B and we add in another factor of distance, this radius distance, that clearly unit-wise is going to turn into area, so that makes sense. But you'll have to hang tight for me to prove this to you in just a second. All right. I should mention, though, before I do that, that there also is another way that people will write this formula, and that is that they will take this I times A, and I times A sometimes gets a special name. All right, so I times this area vector sometimes gets the letter referred to with the letter mu, because we haven't had enough mu's, so don't worry, we got more. All right, the letter mu, so we say this is vector mu. So vector mu is I times vector A. All right, that's vector mu. And this gets a special name. This is called, mu here is the magnetic dipole moment. All right, magnetic dipole moment, that's mu. And so another way that this formula often gets written then is that torque is mu, this magnetic dipole moment, crossed with B. All right, so here's another formula for torque, mu cross B. But remember that mu is just the amount of current you have flowing multiplied times this area vector. So whatever area that current is enclosing, right, whatever area the current loop is enclosing, and the direction being, if you curl your fingers in the direction of the current, what way does your thumb point? All right, so a couple formulas here for torque. Now, it would be nice, though, to sort of know where these formulas come from. So I would now like to try to show this to you, try to at least make an argument that this is the correct formula. And the way I want to make that argument is I want us to sort of take this picture, all right, and let's look at it from sort of a side view. All right, so let's imagine a moment right after it starts to rotate, right? So this force is going to kind of push it down. This force will push it up. And so right after it rotates, if we take, starts to rotate, if we take sort of a side view here, right? This would be sort of its rotation axis, right? Through here, right? That's the axis it's going to rotate around. So here's the rotation axis, the pivot point, if you will. And we have our downward pointing force, right? Our downward pointing force. And we have our upward pointing force, right? And remember that force is I times L times B, right? I times L times B. And it had a sine 90 in it, right? And that 90 degrees is the angle between L and B, right? So L is going like this, B is going like this, and as it rotates, that's not going to change, right? The angle between L and B doesn't change, so this force is always ILB, all right, and always into the page here, okay? Similarly, this force is also ILB, all right, and out of the page, all right, and out of the page. And so now we want to think from these two forces, all right, what is the net torque that we're going to get, all right? So what is the net torque, right? What is, if we sum all of the torques from these forces, what are we going to get when we sum the torques? Well, let's do that, all right? So torque, right, what is our formula for torque? Well, we wrote it down over here. Torque is R cross F. R cross F, so that means we need to know R is the distance from the pivot point. So what is the distance from the pivot point? Well, on our rectangle here, we had side length A and side length B. So if this is side length B, that means that our radius, the distance from the pivot point to F, must be B over 2, right? That side length B, just half of a B, right? Here's our axis, right, is the distance from the pivot to where the force is being applied. So it's B over 2 that way and B over 2 this way. Okay, so we know now that the radius is B over 2, and so for each of these forces, we know that the torque is R cross F, which means it's going to be R times F times the sine of the angle between R and F. So let's think about that. So if R is this way, right, here's my R vector, and that's F, then I'm going to have some angle phi, there, right? And similarly here, we didn't leave very much room. Let's relabel that. So here's my F vector. All right, here is phi, right? That's the angle between my R vector, right? My R vector pointing out this way, that's my R vector, right? And F, right? So the angle between them is phi. And but now F, we said, well, F, okay, so, and we're gonna have two of those, right? RF sine phi for this one, right? Plus another RF sine phi for this force, right? So that's gonna be the net torque is those two things. All right, so, but we should now plug in some numbers or some other variables. So, well, R, we said that's B over 2, right? So, how am I doing on space? I'm doing good. All right, so R is B over 2. So we'll have B over 2. F, we said, is I times L times B. I times L. What is L in terms of the variables? L is this A, right? I said this is A and B, so that's, I'm going to rewrite that as A. And then big B is the amount of magnetic field, right? And then we still have the sine of the angle between them, and it will be the exact same for this term, so I'm actually going to get two of those, which when I add them together, right, that will just cancel this factor of 2. So I'm just going to actually write this as B because this is the same for both terms, and when I add them together, well, no, I should write it out. Let's be clear. So B over 2 plus another one, B over 2 IAB sine phi. And so when we add those together, now we're going to get and I'm going to rearrange the order a little bit here, A, B, big B, sine phi, right? IAB sine phi here. And so, but now what you see is A times B, that is just the area, right? A times B, that's just the area. So now we have that this is I times the area times B times the sine of the angle between them. And the last thing to notice is, well, the area vector, the area vector always points perpendicular here, right? Perpendicular, so that's the area vector. And B was always horizontal, so that's this way. So here's B, the direction of B, right? Or B, like this. And so the angle between A and B, well, that's going to be the large angle here, right? And so phi, this angle is the exact same as this angle here, right? These two are the same angle. So the angle between A and B is the same as the angle between F and R. So A times B times sine phi, well, I could just rewrite that as A cross B. And so what I end up getting from all of this is exactly the formula that we wrote down, that torque must be I times A cross B. So, yeah, anyway, hopefully that just shows you a little bit of where that comes from. I think it's kind of cool. In another video, and I think maybe for next class, we will do some examples of how this could be useful. But you might be noticing now that if I run a current in a loop, right, and I put that in some magnetic field, now I actually get some motion. I get something that rotates, and once I have something rotating, you know, that maybe could be something that I could use, like maybe in a motor, like an electric motor or something like that. So stay tuned, and we'll think about some applications in other videos.